Okay, so I'll be presenting the paper Property Testing Low Bounds via Communication Complexity by Blay, Brody, and Matulev. So in this paper, we will see how communication complexity can provide property testing lower bounds. And some of these lower bounds that we are going to see are going to be tighter than the ones that exist in the literature. But we will mostly get to that towards the end when we reach the conclusions. So just as a reminder, property testing is concerned with testing objects, such as functions, for certain properties, when we have limited access to those objects. So we will be defining this more accurately later on, but this is just a reminder. Now, many techniques were developed for designing such property testing algorithms, and we've seen many of these in class. And these provide us with upper bounds, but we're also, of course, interested in obtaining lower bounds. And these are much more difficult to obtain as they require a for all statement. And we've seen one technique, we've seen Yao's minimax technique, which we used in the when we discussed constant and later on when we discussed var as well. And here we will actually see a new technique to obtain lower bounds using communication complexity. So communication complexity has many techniques for computing low bounds in other areas of computer science. So it stands to reason that it might also be relevant for property testing low bounds. And this claim is actually strengthened even further when we notice that property testing and communication complexity are actually quite similar. They both have parties with unbounded computational power. So on the one hand, we have the tester, and on the other hand, we have the communicating players. And also, both of them involve algorithms by parties with restricted access to their input. So using these similarities, communication problems can actually be reduced to testing problems in order to obtain low bounds, and that's what we are going to see all throughout this paper, this talk. And this work, importantly, is the first to connect between the two fields. So the structure of this talk is going to be as such. We will start with definitions and theorems that we will have to get acquainted with in order to link between communication complexity and property testing. Once we've established all of these, we will move on to the testing low bounds. So we will discuss specifically testing k-Linearity and related properties, testing monotonicity and submodularity, and testing concise representations. And finally, we will also discuss testers with one-sided error. So first, we will discuss definitions for property testing. We're largely familiar with these from class, but we will go through these anyway. So a property of functions. So for a fixed range R in the real numbers, a property P of the functions from 0, 1, n to this range R is a subset of those functions. So the next definition is distance between two functions. So the distance between two functions f and g from 0, 1, n to r is the fraction of inputs x in 0, 1, n for which fx differs from g of x. The distance between f and property p, so this time it's a property, is the minimum distance between f and any function g in this property. Again, we've seen this in class. And epsilon far, when the distance from f to the property p is at least epsilon, we say that f is epsilon far from the property p. So a few more definitions. We have tester. So an epsilon q tester for the property p of functions from 0, 1, n to r is a randomized algorithm that queries a function f from 0, 1, n to r on at most q inputs from 0, 1, n, and it accepts with probability at least 2/3 when f is in p, and rejects with probability at least 2/3 when f is epsilon far from p. We have a non-adaptive tester, which selects the q queries before observing f's value on any of these queries, otherwise it's adaptive. And we have one-sided error. The tester always accepts functions in p. And two-sided error, the tester accepts functions in p with probability p, where p is at least 2/3 and less than 1. The next definition is query complexity of property p. So for epsilon larger than 0, less than 1, we define 3 types of query complexity of p at distance epsilon. So the first one is q epsilon p. This is the minimum value of q, the minimum number of queries for which p has an epsilon q tester. Q1 epsilon p is the minimum value of Q required to epsilon test p with one-sided error this time. For this we have the 1 here. QNA epsilon p is the minimum value of Q required to non-adaptively epsilon test p. So for this we have the NA here. And moving forward, we will assume that epsilon is a small and fixed constant, such as epsilon 0.01, and so we can drop epsilon from the notation. So next we move on to definitions of communication complexity. So first, communication game. So we find a communication game as follows. So Alice and Bob, they receive inputs X and Y respectively, X for Alice, Y for Bob. And their goal is to compute some function f of their inputs X and Y. Now neither of them has enough information, so they have to communicate in order to compute this. And then we are interested in the communication complexity, which is how much communication, for example, how many bits need to be transferred, are needed in order to compute f. And then we have protocol P, which is just a distributed algorithm that determines the messages that Alice and Bob send to each other in order to compute f of x, y. So now that we know what a protocol is, we have deterministic protocols. So a deterministic protocol is defined as such. Each party's messages are simply a function of their own input that they received. So for example, it's going to be, for Alice, it's going to be X, and the previous communication between the parties, between Alice and Bob. The cost of a protocol is the maximum over all inputs, the maximum number of bits communicated by Alice and Bob. And a deterministic communication complexity of f is defined to be the minimum cost of a deterministic protocol computing f, and we will denote it as d of f. Now we have randomized protocols. So a randomized protocol is simply a case where Alice and Bob share access to a random string, which we will write as such, of some length. A delta error protocol, so P is a delta error protocol for f if for any inputs x, y, P computes f of x, y with probability at least 1 minus delta, where the probability is taken over R. And finally, we have one-sided error protocol. We're talking about a binary function here. So P computes f with one-sided error if there exists some z from 0 or 1, such that P computes f with probability 1 when f of xy is not equal to z, and with probability at least 1 minus delta when f of xy equals z. Finally, we have one-way protocols as well. So that just consists of a single message transferred from Alice to Bob, and Bob then outputs an answer. So here is some notation as well. So we have that R delta F denotes the minimum cost of a delta error protocol for F. And when we want to drop the delta and just use 1/3, so we will write it as this. So RF is defined for this specific delta. And we also have RZ delta of F, which is the minimum cost of a randomized one-sided error protocol for F. We call the Z for the one-sided. And again, if we want to drop the delta and use delta 1/3, so we will define it as such. We also have a similar notation for the minimum cost of a randomized delta error one-way protocol for F. So we have this arrow showing us that this is a one-way protocol. Once again, when we drop the delta, we can see that it's written this way. And then we also have a case where the minimum cost of a randomized one-way protocol for F with one-sided error delta. So we can see the two together. We have the one-way protocol, and we have the one-sided as well. And once again, when we want to drop the delta and use third, so we will just simply write it this way. So now we reach the main reduction. So we will obtain lower bounds for property testers through reductions from communication games that have known communication complexities, of course. So the communication games actually make use of what we call a combining operator. So an operator, psi, will be a combining operator if it takes as input two functions f and g from 0, 1, n to some z, and returns h from 0, 1, n to some r. So we denote the communication game that uses the combining operator psi that we just defined to test property P as CP psi, and we define it as such. So Alice receives F, Bob receives G, and their goal is to compute CP psi of F and G, which is defined to return 1 if psi of Fg is in P, and 0 if psi of Fg is epsilon far from P. Now, how do we reduce from a communication game as the one we just defined to a property testing algorithm? So what we'll do is Alice and Bob will solve CP psi by emulating actually a p-testing algorithm on H, which is defined as such using psi. So communication between Alice and Bob has to occur, as we said earlier, because H depends on both F and G. So neither of them have enough information to compute H on their own. So they have to communicate. So in order to obtain a strong query complexity lower bound, we want the joint computation of H to be as communication efficient as possible. And this is accomplished using what we call a simple combining operator, which we will now discuss. So a combining operator psi is called simple if for all fg and for all x, the query h of x can be computed given only x and the queries f of x and g of x. So an example for that would be h of x defined to be fx XOR gx, where fg are Boolean functions. Okay, so this is simple because it depends only on x and the queries f of g and g of f of x and g of x. So now we're ready to discuss the main reduction lemma, lemma 2.4, and then we'll be seeing this in use all throughout the paper, so it's very important. So a fixed set to be a finite set. So for any simple combining operator psi for functions f, g from 0, 1, n to z and any property p, we have the following relations between the communication complexity, complexities that we defined earlier and the query complexities that we also defined corresponding to the communication complexities. So this side is for the testers and this side is for the communicating complexities. So we'll prove each one of these, but we'll be starting with number 3 because it will open the doors for the remaining ones. Okay, so we're starting, as I said, with number 3. So we have a case of non-adaptive testers and one-way protocols. So what we'll do is we'll set A to be a Q query, sending Q queries, non-adaptive tester for P. And what we'll do is we'll create the following one-way protocol P for CP psi. So it's going to be Alice and Bob will be generating Q queries using some public randomness. And then Alice computes the values for the queries, so fx1 through till fxq. And then what she does is she sends it in bulk to Bob using Q log z. Log z is the bits per one query that she'll have to send, and these are the number of queries. So this is the total number of bits that she would have to send, and we can see that for z that would have 0, 1 only as possible outputs, it would just be q bits that she has to send. So then what Bob does, he computes similarly to what Alice did. He computes his own values, gxi, from 1 through q for each one of the queries. And then because he has Alice's values as well, he can compute hxi for each i from 1 through q. Then what he does, he just emulates A using these values that he just computed, hx1 through hxq, and he outputs 1 if and only if A accepts h. So what we can see is that if A has a two-sided error, the way we defined it earlier, if you can recall, that means that P also, he just computes CP psi with probability at least 2/3. Which gives us this relation because we have the communication complexity is less or equal to the number of queries times by the upper bound of the size of the message per query. So that's Q upper bound log Z. And of course, if A is optimal, then we get that we can just plug in Q to be the Q non-adaptive for this property, and then we just got the relation that we were looking to obtain. So now we can easily move on to prove number 4. It's pretty straightforward. So if A has one-sided error, in which case you should recall that it always accepts functions in P. This is how we defined it earlier. So P computes CP psi with probability 1 when H is in P. We're using the same protocol as before, so this is, once again, this is straightforward. And then P computes CP psi with probability at least 2/3 when H is epsilon far from P. And this is because A is one-sided error, as I said. So therefore we get this relationship. It's the same thing. So we have a one-way protocol with one-sided error, and it's less or equal to Q upper bound the number of bits per message. And of course, once again, if A is optimal, then we can plug in Q equals Q non-adaptive one-sided, and then once again we complete the proof that we were looking at to obtain. So to prove number 1, notice we no longer have one-sided or non-adaptive. So let A be a Q query adaptive tester for P, just as before, but we have now an adaptive tester. So what we can do is we create the following two-way protocol P for CP psi. And it's going to be as such. So Alice and Bob, what they do is they generate one at a time. This time it's one at a time, not in bulk, queries x1 and xq using some public randomness. So for each query xi, what they do is they exchange fxi and gxi. Okay, so it's not as before where Alice could send it in one go. They have to exchange it now for each query. And then they compute hxi, which is once again h of fxi gxi. And then they generate the next query based on all prior computations. Now they repeat this until they have hxi for every one of the queries that they got. Now once they've done this and they have all the queries, so Bob can emulate A using hx1 through hxq, and he outputs 1 if and only if A accepts h. So what we have is that for each query we have 2 log z bits must be communicated, so that's because they each communicated per query. We had both Bob and Alice sending their results, so in total for all the queries we have 2q upper bound log z. And of course, if A is optimal, an optimal adaptive tester with two-sided error, so what we get is that P computes CP psi with probability at least 2/3, and therefore we have that the communication complexity is less or equal to twice the number of queries times by the bits, upper bound bits per query. So now we are ready to move on to the proof of number 2. So given the proof that we have just seen, this is going to be pretty straightforward. The only difference is that we have one-sided errors in this case. So if A is an optimal adaptive tester with one-sided error, which I'm reminding means that it always accepts functions in P. So the protocol P computes CP psi with probability 1 when H is in P. I'm reminding that CP psi returned 1 if and only if A accepted H. And P computes CP psi with probability at least 2/3 when H is epsilon far from P. So this matches the requirement that it only makes errors when the outcome is 0. So then we immediately get the same relation that we saw before. Okay, so now we are ready to discuss some communication complexity problems, the ones that we're going to be using for to perform the reductions. So there's going to be a list of some problems that we will be looking at. Some of the lower bounds will be taken from the literature, and some we will prove along the way. So the first communication complexity problem is set disjointness. So in this problem, Alice and Bob are given n-bit strings x and y. So this is Alice's input and this is Bob's input. And their goal is to compute the following functions. So we can see bitwise AND operation and or across all the bits. So X and Y, we will sometimes treat them as sets of indices from 1 through n, subsets of these of 1 through n. And in this case, we will say that disjoint n of AB is 1 if and only if the intersection is not empty. Okay, so we'll sometimes treat it as sets. So from the literature, what we have that the communication cost of disjoint n is omega n. Okay, so we'll be using this relationship. And we will also be talking about a specific version of this problem, which is called the balanced version, k-balanced disjoint. We'll see this appearing later on. So this is the name that we will give this type of sub-problem. In this case, Alice receives a subset of n of a specific size, which is lower bound k over 2 plus 1. So it's roughly the same size as Bob's, which receives also a subset of 1 through n of size upper bound k over 2 plus 1. So that's why it's called balanced. Okay, it's relatively balanced in the sizes that they receive. And in this case, we assume that it is guaranteed, as promised, that the intersection of A and B, the sets that they receive, its size is at most 1. So it's either 0 or they intersect on 1. So we will now see the following lemma. So for all k at least 0 and less or equal to n minus 2, the communication cost of k-balanced disjoint is omega of minimum k and n minus k. So we will now prove this lemma because we want to use this lower bound in our future reductions. So of course, if n minus k is O of 1, then it's trivial, so there's nothing to prove in terms of the lower bound. So we'll assume otherwise. So in this case, we'll set m to be the minimum between the lower bound of k divided by 2 plus 1 and n minus k minus 2. So we'll soon see why we're doing this. So what we'll do, we'll actually reduce from disjoint m, which we just saw earlier that we know from the literature the lower bound on this problem. So what we will be doing is we'll partition the indices of 1 through n without the indices of 1 through m. So that means what's left after we remove these indices into two disjoint subsets. So the first one is going to be, well, we're going to denote it with I, so that's going to be m plus 1 all the way through to m plus 1 plus k over 2 lower bound. And the second one is going to be from 1 plus this all the way to n. So we can see that these two together are basically what's left after we remove 1 through m all the way to n, and we just split them into two disjoint sets. Okay, so they don't have any shared elements. So another thing we should notice is that the size of I is k over 2 lower bound plus 1, and the size of j is at least k over 2 upper bound plus 1. Now, these two are simple algebra. This is really pretty straightforward. This is slightly more involved, but we'll quickly look at this in the next slide. So for the size of j, we just take the last element minus the first element plus 1. Okay, and we do some simple algebra. This transition is just because k equals the sum of these two elements. Okay, and here we have, again, just equality from simple algebra. And the transition from this equality to the larger and equal to this statement is simply because m is the minimum of some element that we defined, and n minus 2 minus k. So of course it's going to be smaller or equal to n minus 2 minus k, which means that this whole statement is going to be larger or equal to 0. So then if we eliminate it, we get the following relation. So this is pretty straightforward. So now we can continue the proof. So the input to disjoint M is A prime and B prime. So these are the sets that are received by Alice and Bob, respectively, for disjoint M. And then what Alice does is that she pads her input with elements from I, okay, until it reaches the desired size that we need for our reduction, which is k over 2 lower bound plus 1. And the way she does it is she takes a prime, and then she adds m plus 1, and so on until she reaches the desired size. Okay, so A is actually k over 2 plus 1 minus what she already had, the size that she already had. Okay, so we can see that this is her new input that she's generating. And Bob does the same thing, but he does that from J. Okay, so he takes elements from the end all the way until n minus b plus 1, where b is once again what the size that remains after he eliminates the size of b prime, which is what he received. Okay, so he ends up also with the desired size that we need for him, which is k over 2 upper bound plus 1. And of course we can see that the intersection of A and B is exactly the intersection of A prime and B prime, simply because, as I mentioned before, these two are disjoint. So now we can see that a solution for k-balanced disjoint of A and B provides a solution for disjoint M using A prime and B prime. Okay, so then that's how we get the reduction. So the communication cost of k-balanced disjoint is at least as large as the communication complexity of disjoint M due to our reduction. And this we know from the literature we saw earlier as omega M. And because of our definition of M, we receive that it's equal to omega minimum of k and n minus k. So now we reach another communication complexity problem that we'll be using for our reductions later on, and this one is gap equality. So in this case, Alice and Bob are given n bit strings x and y, once again respectively. So from now on, if it doesn't mention explicitly, Alice's is x and Bob is y. And their goal here is to compute GEQ with parameters nt for xy, which just means that if they are equal, so it outputs 1, and if the Hamming distance between them is t, then they output 0, and otherwise it can be either 0 or 1. Okay, so that's what the star here means. So often we'll be using a default t, so that's going to be n divided by 8, so if we don't state otherwise it's going to be this value. And of course, as I mentioned, when GEQ xy equals star, that means that the protocol can output 0 or 1. And what we're interested in this case is the communication cost that makes errors only on Z. Okay, so as I said, this is the definition for the minimum communication cost of a protocol for GEQ that makes mistakes only when GEQ equals Z. So we know from the literature, we'll call this Lemma 2.7, that the communication cost that makes errors only on GEQ1 is omega n for all even t that is theta of n. So we'll be using this lemma later on. So now we have also the gap Hamming distance. So in this case, Alice and Bob were given n-bit strings again, x and y. And the goal in this case is to compute GHD with parameters n and t, which basically just says that if the Hamming distance is at least as large as n over 2 plus some t, this t here, then they output 1, and if the Hamming distance between them is less or equal to n over 2 minus t, then they output 0, and otherwise, once again, they can output any value of 0 or 1. Here too we will have a default value for t, so if we don't mention it explicitly, it's going to be the square root of n. As I said, when GHD xy equals the star sign, that means that the protocol can output 0 or 1. And also in this case we have the option that x and y can be subsets of the indices 1 through n, in which case we will use the size of the symmetric difference between A and B, and that's going to be instead of the Hamming distance between x and y. And for this problem, we'll be using both the communication cost of GHD and the communication cost for a protocol that has one-sided error on Z. Okay, so this is going to be the minimum communication cost of a protocol for GHD with two-sided error, and this one is going to be with one-sided error on Z. So for the two-sided error case, we're going to call theorem 2.8 to be the one that states that the communication cost for GHD is omega n. This is from the literature, so we'll refer to this as theorem 2.8. And we also know from the literature that the communication cost of GHD nt is omega of n divided by 2 squared. For all t, that is omega of squared n. So for the one-sided error, we'll actually see and prove the theorem 2.9. So for every z in 0 or 1 and every constant delta between 0 and half, we have that the communication cost that makes errors only on z of GHD n delta n is omega n. And we'll actually prove this also for the case of communication cost that makes errors only on 0, and also for the communication cost that makes errors only on 1 separately, and we'll use these lower bounds in different cases later on. So to prove the theorem of communication cost one-sided on that makes errors only on 0, so we'll do the following. So let d be the smallest integer that is still at least as large as delta n, that's our t here, delta n, and we'll set m to be half the size of n plus this d. So now we'll say that P is a protocol for GHD that makes errors when GHD equals 0. So we'll actually do a reduction from GEQ with m and 2d, so that's the t of the GEQ, and it's going to be 2d. So the way we'll do it, we'll use actually P to construct a protocol P prime for GEQ that makes errors only when x equals y. So the inputs to GEQ M2D are going to be x, y that are just strings, binary strings of length m, okay, as we require here. And Alice and Bob will construct x hat, which is defined to be the x that they received from the input, concatenated with n minus m zeros. That's going to be for Alice. And for Bob, he'll do the same thing, but instead of concatenating n minus m zeros, he's going to concatenate the exact opposite of n minus m ones. Okay, and then what they do is they output p prime xy, which will be defined to be 1 minus the p of x hat y hat. And p is from GHD, of course, as we said earlier. So if x equals y, what we can see is that the Hamming distance between x hat and y hat equals n minus m because of the added bits. Okay, they are the same on those that we did not add, and they differ on those exactly that we did add. And this equals n minus, because of the definition of m, n divided by 2 plus d. And this equals n divided by 2 minus d, which is less or equal to n divided by 2 minus delta n because of the relationship between delta n and d that we defined earlier. So therefore, we can see that GHD of x hat and y hat, because of this, is 0, and GEQ of xy is 1 because of this. Conversely, if the Hamming distance between x and y is 2d, so the Hamming distance between x hat and y hat is 2d plus n minus m, okay, what they were different on before we added the bits and the added bits, and this equals 2d plus n divided by 2 minus d. And this we get n divided by 2 plus d, which is larger or equal to n divided by 2 plus delta n, again because of the relationship between d and delta n. So therefore what we get is that GHD of x hat and y hat equals 1, okay, because of this, and GEQ of xy equals 0. So because p prime equals 1 minus p, we can see that p prime correctly outputs GEQ for xy whenever p correctly computes GHD for x hat, y hat. And we also can see that the way we defined P, it makes errors only when GHD of x hat y hat equals 0. So this corresponds to P prime only making errors when GEQ of xy equals 1. And so we get the reduction relationship that we were looking to prove, and we know that the communication complexity one-sided that makes errors only on 1 for GEQ with our setup is omega of m. Okay, we saw this before, and the way we defined m, we obtain that it equals omega of n, and we get our reduction proof. Okay, so now we will see the other side, which is when the protocol makes errors only when the GHD output is supposed to be 1. So we'll actually use the results that we saw in the previous proof. We'll actually reduce from R0, which we just saw, GHD, by simply noticing that GHD of xy equals 1 minus GHD of x 1 minus y. So we're just flipping the bits here. So whatever they were different on, they become similar on, and so it makes sense that the output would also flip. So in this case, Alice and Bob will run a protocol for GHD that makes errors only when GHD equals 0. And they'll do so by computing GHD of x 1 minus y, which is what we wanted here, and simply inverting the output to be 1 minus the output from this computation. So we're just basically getting this relation that we wanted. So it's pretty straightforward. And what we're getting from this is that the communication cost, the minimum communication cost when the protocol makes errors only on GHD equals 1 is at least as bad as the minimum communication cost when it makes errors only when GHD is supposed to be 0, which we just proved to be omega n. So now we will be talking about the extended gap Hamming distance. This is another communication complexity problem that we will be using its lower bounds later. So in this extended version, extended GHD, so we'll write eGHD for that. In this version, we have n and t as before, and we also have k. So in this case, Alice and Bob are given n bit strings. Again, Alice gets x, Bob gets y. And in this case, their Hamming weight, which is the number of ones in each one of the inputs, equals k. And their goal in this case is to distinguish between the Hamming distance being larger or equal to k plus 2 and the Hamming distance being less or equal to k minus 2. So more formally, we can see eGHD here being a function with parameters nkt of x and y. And again, we can see if the Hamming weight is larger or equal to k plus 2, they should output 1. And if it's less or equal to k minus 2, they should output 0. And once again, any other case, it can output either 1 or 0. So here we have lemma 2.10. So we're going to say that for all kt less or equal to n divided by 2, we have that the minimum communication cost for eGHD nkt is omega of the minimum between k divided by t squared and k. So we'll prove this lemma, and we'll first prove it for k equals n divided by 2, and then we'll use this result along with a padding argument in order to prove it for the general k. So now we will prove lemma 2.10, again for the case k equals n divided by 2, and we'll actually do a reduction from the gap Hamming distance with n divided by 2 and t divided by 2 instead of n and t, which we saw in the definition. So we'll define P to be a protocol for the extended gap Hamming distance with n, t, and instead of k we have n divided by 2. So given the inputs x hat and y hat, which are binary vectors of length n divided by 2. These are the inputs to GHD n divided by 2, t divided by 2. What Alice and Bob will do, they will create n-bit strings. Okay, they'll inflate it to be n length. N-bit strings x and y, Alice is x and Bob is y, by simply mapping any zeros to be zeros and ones, 0 and 1, and any ones to be 1 and 0. Okay, so they actually not only inflated, they not only doubled the size to become n instead of n divided by 2, but they also doubled the Hamming distance, because we can see that if they were different with 0 and 1 before only, so now they are not only different between 0 and 1, but also they're different between the 1 and 0 that we added. So what they do with this, they simply run the protocol P on x and y, and they output the result. So we can see that the Hamming weight of x equals the Hamming weight of y and equals n divided by 2, which is rk. And this is because every original bit in x hat y hat got 1 0 and 1 1. Okay, this is from the mapping that I explained in the previous slide. We can also see that the Hamming distance between x and y is twice the Hamming distance between x hat and y hat, and then again this is what I explained in the previous slide, again from the mapping. And therefore we can see that if the Hamming distance between x hat and y hat is larger or equal to n divided by 4 plus t divided by 2, then we can see that we get the Hamming distance between x and y, which is twice the Hamming distance between x hat and y hat, okay, we just said this, is greater or equal to n divided by 2 plus t. Conversely, if the Hamming distance between x hat and y hat is less or equal to n divided by 4 minus t divided by 2, then we get that the Hamming distance between x and y, which is twice the Hamming distance of x hat and y hat, is less or equal to n divided by 2 minus t. So therefore, what we get is that correctly computing the extended gap Hamming distance with n, t, and k being n divided by 2 gives us a correct response to the gap Hamming distance with parameters divided by 2. So therefore, we got that the minimum communication cost of the extended gap Hamming distance with our parameters is at least as costly as the as the communication cost of the gap Hamming distance with n divided by 2 and t divided by 2, which we saw earlier can be either n divided by t squared or n, which this was in the case where we saw that it was omega of t being omega of squared n, so that was one of the lemmas that we saw earlier, and another one that we saw earlier was that it was omega of n. For a general t. So we get that it can be that it is the omega of the minimum between the two, and because n depends on k in our case, except for a constant, we get that it's omega of minimum k divided by t squared, and k again depending on whether t is omega of square root of n or not. So now we can move on to the general k. Previously we saw k being equal to n divided by 2, so it's very simple to extend this to a general k that is less than n divided by 2. Simply by doing a reduction from the extended gap Hamming distance with 2k and kt to the extended gap Hamming distance with n, k, and t. What we'll do is we'll use a simple padding argument. In this case, what Alice and Bob do is they receive a 2k bit string each. So Alice gets x hat and Bob gets y hat. And Alice simply constructs x, which is x hat with n minus 2k zeros concatenated to the end of it, and Bob constructs y very similarly with y hat and n minus 2k zeros concatenated to y hat. So what we can see is that the Hamming weight of x and y, they are equal once again and equal to k. Again, this is the number of ones that they have, so of course this remains the same because we only added zeros. So the Hamming distance between x and y is exactly the same as the Hamming distance between x hat and y hat, of course, because the only thing that we added is zeros, and they're identical on those zeros, so of course the Hamming distance is the same. And therefore we get that the answer to extended gap Hamming distance with n, k, and t provides an answer to the extended gap Hamming distance with 2k, k, and t. And therefore we get that the minimum communication cost of the extended gap Hamming distance with the desired parameters is at least as large as the communication cost for the extended gap Hamming distance with 2k and k. Notice, of course, that this means that we're in the case of k being equal n divided by 2. N here is 2k. So this we saw earlier, and this is omega of the minimum between k divided by t squared and k, as I explained before, depending on whether t is omega of square root of k in this case. So now we will be talking about the testers. Specifically, we're going to be talking about testing k-linearity and related properties. So before we do that, we have to mention a few definitions. So the first one is k-linear functions. So that's just as we saw in class, a function of the form fx, which is a sum of xi, I in s modulo 2, where s is some subset of 1 through n, indices 1 through n of size k. So that's a k-linear function. And k-hunter, again, as we saw in class, a function from 0, 1, n to 0, 1 is a k-hunter if there exists some subset j of 1 through n that has size at most k, such that for every xy in 0, 1, n that satisfy the following condition, which is that for all I in j, if xi equals yi, then we have fx equals fy. So basically all it means is that it's a function that depends on at most k variables. So next we have the Fourier degree. So before I go into the definitions for Fourier degree, I'll just mention that the domain here is slightly different to what we've seen in class. We had a mapping in class from 0 to 1 and from 1 to -1. And so I've left the domain as the authors left it, and that means that we are looking at this chi-s instead of what we've seen in class. So for Fourier degree, we have that every Boolean function f from 0, 1, n to -1, 1 has a unique representation as follows. Again, this is very similar to what we've seen in class, where chi-s is of this formulation, and f hat s is the Fourier coefficients of f. Finally, the Fourier degree of f is the maximum k at least 0, for which the Fourier coefficient is not 0 for some set with size k. So finally we have k-sparse. So every Boolean function f from 0, 1, n to 0, 1 has a unique representation as a polynomial over f2. Okay, so this is also known. And if, f is k-sparse polynomial if its representation over f2 has at most k terms. So that's when we say that it is a k-sparse polynomial. So moving forward, we will be using the following notations. So k-linear, when it's written like this, means a function is k-linear. K-hunter for a function that is k-hunter. Degree k for a function that has Fourier degree at most. Okay, and k-sparse for a function that has a k-sparse f2 representation. So we now have proposition 3.4. So fix n larger than 2 and k between 1 and at most n minus 2. So if f from 0, 1, n to 0, 1 is a k plus 2 linear function, then f is half far from k-linear functions, half far from k-hunters, half far from functions of Fourier degree at most k, and 1/20th far from k-sparse polynomials. Now this is based on the literature, but we will prove the remainders. So now we will prove number 3. So let f be a k plus 2 linear function over t, which is a subset of the indices 1 through n of size k plus 2. And let g be a function of Fourier degree at most k. And we say that f and g are functions from 0, 1, n to -1, 1. So f is a linear function, as we said, over the variables in t. And therefore, for every s that's different to t, we have that f hat t equals 1 and f hat s equals 0. Now, if we want to briefly recall from class why this is so, then we can notice that the definition, as we saw in class, of f hat s equals the expected value over x for fs chi s, and in this case they have -1 to the power of the sum of variables. Here we also have the sum of variables, and if we use our mapping from class, which maps from 0 to 1 and from 1 to -1, we can actually see that for t, these two will always be identical. Okay, if the power here is even, and we're talking modulo 2 of course, and the sum here is also identical to the power, which will mean that it's also even, then these two will be identical. If it's odd, they will also be identical. So for t, it's going to be identical. For s, different to t, then there will always be one, and one of these will always have at least one missing variable, and then half the time these two will yield, the multiplication will yield 1, and half the time it will yield -1, and so we will get 0 for the expected value. Finally, G has Fourier degree k, and we know that the size of t is larger than k. Okay, the size of t is larger than k. So by definition, of course, then we know that G hat t equals 0. Okay, because t is larger than the Fourier degree k, which G has. So it cannot be that it's not 0. So by Parseval's theorem, which we have also seen in class, we have that the expected value over x for fx gx equals the sum of the subsets in 1 through n of the Fourier coefficients of f and g for s, and that this is equal 0. And the reason this is equal 0 is very simple. We can just split into cases whether s equals t or not. So if s equals t, then we just saw that g hat s for s equals t is 0. We just saw that at the bottom of the previous slide. And if s equals t, also we saw in the middle of the previous slide that in this case f hat s equals 1, and for anything outside of t it equals 0. So again, if s equals t, then this is 0, and if s does not equal t, then this is 0, and so we get that this sums always to 0. So this implies that the probability that fx is not equal to gx is half. Now why is that? Because fx and gx can only get values from -1 and 1. So if we can see that the expected value is always 0, that means that half the time they have to have the same sign, and half the time they should have different signs. And so indeed we get that the probability that they don't have the same sign is half. So therefore we have that f is half far from g. So to prove 1 and 2, we just need to notice that k-linear and k-Cont functions have Fourier degree at most k. And so the proof for number 3, which we just saw for Fourier degree at most k, immediately applies to 1 and 2 as well. So now we'll talk about the main theorem, which is theorem 1.1. So we fix k to be between 1 and n-1. So at least omega of minimum k n minus k queries are required to test k-linear functions, k-Contas, functions of Fourier degree at most k, and functions with k sparse polynomial representations in F2. So we'll now prove this. So we'll reduce from k-balanced disjoint. So we'll define the following communication game with property k-linear and combining operator XOR, where Alice and Bob get f for Alice, and g for Bob from 0, 1, n to 0, 1 as their input. And their goal is to determine if h, which is the XOR of f and g, is k-linear or far from k-linear. So we'll recall from Lemma 2.4, which we have proven, this relationship between the query complexity for testing some property and the communication complexity of the corresponding communication game. So if we apply this relation to our communication game, we get pretty much the same thing. In our case, this is z, so this is log of 2, which is just going to be 1. So it disappears, and we get the same relation. So from Lemma 2.6, we also have proven that the minimum communication complexity of k-balanced disjoint is omega of minimum k and n minus k. So it seems that all that we have left to show is somehow to combine, to relate between these two in order to get the lower bound for the communication, for the testing complexity. Okay, we want to show that this is also omega of this. So just to formally state it, it remains to show that the minimum communication cost of our communication game is at least as expensive as the minimum communication cost of k-balanced disjoint. So we'll reduce from k-balanced disjoint. Alice and Bob receive A and B, which are subsets of 1 through n. Of size, A is going to be the size that is required for k-balanced disjoint, which is k divided by 2 lower bound plus 1. And for B, also we want it to match the input for k-balanced disjoint, so it's going to be upper bound k divided by 2 plus 1. And what they do is they construct parity A and parity B from 0, 1 and 0, 1, where we find parity of Sx to be the XOR of xi, where I is in S. Now we should notice that parity A XOR parity B is the same as writing parity A without B XOR parity A intersection B. This is for A XOR, this is this XOR, with the same kind of split for B as well. So we have B split into the intersection with A and B without A. And what we can see is that these two are equal all the time. It's the same thing. So this is always going to be 0, and so we're going to be left with simply the XOR of the symmetric difference between A and B. So this is going to be useful in the next slide. So when the intersection between A and B is exactly 1, they intersect on exactly one element, what we see is that the size of the symmetric difference is, of course, the size of A plus the size of B minus twice the size of the intersection, of course, because they both have this element. And we get that this is equal k from the definition of how we defined A and B. And therefore what we get is that parity A XOR parity B, which we saw is parity symmetric difference between A and B, is k-linear. Now when the intersection is empty, what we get is that this symmetric difference has size k plus 2, and therefore the parity of the symmetric difference is actually k plus 2 linear. And what we know from proposition 3.4 is that a k plus 2 linear function is half far from a k-linear function. We proved this. So what Alice and Bob can do is they can use their protocol for this communication game in order to solve their instance of k-balanced disjoint. And then we immediately get this relation that we were looking to obtain, which is this one. So we can do the same reduction using the corresponding communication games for k-junta, for degree k, and k-sparse. So we'll define them as such. So these are communication games where Alice and Bob are given Boolean functions f and g and must decide if h, which is f XOR g, is a k-junta, has Fourier degree at most k, or can be represented by a sparse f2 polynomial. So we'll observe that Alice and Bob created parity of the symmetric difference between A and B, which was either k-linear or k plus 2 linear, depending on the intersection, whether it was 1 or empty, and we saw that earlier. Now, keeping that in mind, we saw that k plus 2 linear functions, by proposition 3.4, we saw k plus 2 linear functions are half far from k-juntas and functions with Fourier degree at most k, and 1/20th far from k-sparse polynomials. So also noting that a k-linear function is a k-junta, has Fourier degree at most k, and can be represented by a k-sparse polynomial, what we can see is that Alice and Bob can use their protocols for any of these communication games in order to solve their instance of k-balanced disjoint, and so we immediately get the same kind of relationship as we saw with k-linear. We get it for these communication games as well. So in total, combining with Lemma 2.4 and 2.6, 2.6 was for the k-balanced disjoint complexity, and 2.4 was for the query versus the communication complexity. So in total, we get the following relations between the query complexities of testing these properties and the communication complexities of the corresponding games, which we just saw is equal to omega of minimum k n minus k, which was derived from k-balanced disjoint. So we complete our proof for 1.1. So now we'll move to theorem 1.3. So this states that testing the class of linear functions from f3n to f3 that have only 0, 1 coefficients requires theta of n queries. Now the proof, the upper bound is known from the literature by Goldreich, and the lower bound we will now prove by a reduction from set disjointness. So we'll denote by C plus 0, 1 linear the communication game in which Alice and Bob receive again F and G respectively from F3n to F3. And their goal is to determine if H, which is the pointwise sum over F3, F plus G we'll write, is linear with only 0, 1 coefficients. Now by Lemma 2.4 again, we have the following relation between the query complexity of 0, 1 linear and the communication complexity of the testing game for 0, 1 linear, where the 4 instead of the 2 is simply because we now have z being of size 3, so the upper bound of log z will be 2, so it's 2 times 2 and we get the 4. Now by Lemma 2.5, the communication complexity of disjoint is omega n. And so, just as before, it remains to show that the communication complexity of this testing game for 0, 1 linear is at least as costly as the communication cost for disjoint. And then we get the desired relation. So we relate between these two. So we'll do a reduction from set disjointness to 0, 1 linear. So Alice and Bob receive input to set disjointness, so it's 2 strings for Alice and Bob from in 0, 1, n. And what they do is they build f and g from f3n to f3 respectively, and these are just going to be the following. So it's going to be the sum with the coefficients ai, xi, and the sum with the coefficients bi, xi, of course from I to n. And h, which is the pointwise sum from of f and g, is defined formally as follows. So we just pointwise sum the coefficients for each xi. What they do now is they run their protocol for the communication game to test 0, 1 linear with this function. And this communication game tests if h is in 0, 1 linear or epsilon far from 0, 1 linear. So from the definition of h that we saw just now, we can see, of course, that h is linear, first of all. And also when a and b are disjoint, then the sum of ai and bi is, of course, in 0 and 1. It cannot pass 0 and 1. However, when a, b are not disjoint, ai plus bi equals 2 for some I in the indices from 1 through n, simply by the definition of being not disjoint. So in this case, what we can see is that for any linear function L with 0, 1 coefficients, h minus L is definitely not going to be the identity 0 function over F3. This is, of course, because one of the coefficients will be 2, and here we only have 0s and 1s. So, of course, we'll end up with h minus L having at least one variable with a coefficient that is not 0. So, from the Schwartz-Zippel lemma, we know that the non-zero linear functions over F3n can get 0 on at most 1/3 of the inputs from F3n. So what that gives us when we look at this is h minus L is a non-zero linear function. It's not the identity 0 function. So we can use the Schwartz-Zippel lemma and understand that h has to be 2/3 far from all linear functions like L here with only 0, 1 coefficients. So that would be L for us, and therefore the probability of h of x being different to L of x is at least 2/3. Okay, so h is 2/3 far from all linear functions with 0, 1 coefficients. So when a and b are disjoint, so h is in 0, 1 linear, and when a and b are not disjoint, h is epsilon far from 0, 1 linear. So what Alice and Bob can do is they can run their protocol for testing C0, 1 linear to solve their instance of set disjointness. So that gives us exactly the relation that we were looking to obtain earlier, and therefore we complete the proof. So now we will discuss testing monotonicity. So first we'll define what a monotone function is. So the function f from 0, 1, n to r is monotone if for any two inputs x, y in 0, 1, n, for which x1 is less or equal to y1 and so on until xn is less or equal to yn, we have that fx is less or equal to fy. So now we will show theorem 1.6 and prove it. So this theorem states that testing f from 0, 1, n to r for monotonicity requires omega of minimum between n and the squared size of the range queries. So we will split the proof into 3 cases. The first one is that the range is all the real numbers. Case 2 is that the range satisfies the following condition. Its size is larger or equal to this value. And case 3 says that the range satisfies its size being little o of square root of n. So we'll start by proving case 1 for the real numbers. So the way we'll do this again, we'll perform a reduction from set disjointness. So we will set psi as the following combining operator. So given two functions f, g from 0, 1, n to minus 1, 1, psi will return the following function, which is h from 0, 1, n to the integers, defined as h of x being equal to twice the Hamming weight of x plus fx plus gx. So we'll define the following communication game, C mono with psi, to be the communication game where Alice and Bob receive f and g, f for Alice, g for Bob, from 0, 1, n to minus 1, 1. And the goal is to test whether h that we just defined here, is monotone. So, of course, by Lemma 2.4, which we are very well familiar with by now, we know that twice the query complexity of mono is at least as expensive as the communication cost for C mono psi. This is by the main Lemma 2.4. And by theorem 2.5, we have seen that the minimum communication cost of disjoint n is omega of n. So in order to get a lower bound for the query complexity of testing mono, we need to relate between these two. And so basically it remains to show that the minimum communication cost of C mono psi is larger or equal to the communication cost of disjoint n. So how will we do this? So let A and B be subsets of 1 through n, be the inputs to set disjointness that Alice and Bob receive, Alice and Bob. And what they do is they build the functions chi-a and chi-b from 0, 1, n to minus 1, 1 as follows. We've actually seen this function very recently. So Alice builds this one, minus 1 to the power of sum over the indices that she got, xi. And similarly, Bob does the same with his indices. So h, which is psi of chi-a, chi-b, gives us the following as we defined h before. So we have twice the Hamming distance of x plus f in this case is chi-a of x, and g in our case is chi-b of x. G of x, of course, and f of x. So Alice and Bob run their protocol for C mono psi to solve their instance of set disjointness. So in order to prove the correctness of this algorithm, we need to prove two claims. So claim A will be that when A and B are disjoint, H is monotone. And claim B will be that when A and B are not disjoint, H is 1/8 far from monotone. And therefore, it will be correct to use their communication protocol for C mono with psi. So we will now prove claim A. When A and B are disjoint, H is monotone. So to accomplish this, we'll fix I, some index in 1 through n. And for x in 0, 1, n, we'll set two different x's, x0 and x1, also from 0, 1 to n, very simply by first taking them to be x, and then looking at the ith bit in each one, and setting for x0, setting the ith bit to be 0, and for x1, setting the ith bit to be 1. Okay, therefore it's called x1, and here it's called x0. So for any set S that is a subset of 1 through n, we can see the following two relations. So if I is in S, we have that chi S x1 is the negative of chi S x0. And that's very simple because chi S is minus 1 to the power of all the x, a sum of xi, I, and s. So if one of them includes an extra 1 in the power, we'll have that in one case, one of them has an even power and the other one has an odd power. So minus 1 will be once to the power of something even, and the other time it will be to the power of something odd. So of course they'll have different signs. And of course, if that's not the case, then we have that they have equal signs. So we are in the case when A and B are disjoint, and we want to show that H is monotone. So specifically, we have that I is not in the intersection of A and B because they are disjoint. And we will want to show that H is monotone on each edge, x0, x1 in the ith direction. So one of the options of I not being in A intersection with B is when I is not in A and also I is not in B. We will soon see other cases. So in this case, if we subtract h of x1 from h of x0, sorry, from h of x1, then we would expect this, if it is monotone, if h is monotone, we'd expect this to be larger or equal to 0. So indeed, if we plug in the details into h's formula that we saw in the previous slides, so we get the following term, okay? And what we can see here is that because I is not in any of these sets, we have that chi a of x1 equals chi a of x0. We just saw that at the bottom of the previous slide, and so these two cancel out. And also, of course, I is not in B, so by the same reasoning, also these two cancel out because they are equal. And so we are only left with these terms. Now, the Hamming weight of x1 is only 1 plus the Hamming weight of x0, and so we are left with this being equal to 2, which is, of course, greater than 0. So far, so good for the monotonicity of H. Now, if we write it concisely, so again, we have that h of x1 minus h of x0 in this case is larger than 0. So far, so good, because that seems that H is monotone on this edge of x0, x1. Okay, so what other option do we have for I not in the intersection of A and B? So another option is that when I is in A, but I is not in B. So in this case, once again, we plug in all the details just as before, but in this case, we can see that the difference is that we're still left with the term for chi a x0. And why is that? Simply because in this case, I is in A, and we saw 2 slides ago that when I is in some set S, some subset S of 1 through n, then we have that chi a of x0 equals minus the sign of chi a x1. And so all we did was we just plugged in, instead of chi a x1, we plugged in the minus of the chi a x0, and so we are left with twice chi a x0. Instead of it cancelling out like in this case, we are left with it twice. And we can of course see that for B, this term is cancelled out. Still, in this case, we also have once again that it is larger or equal to 0, simply because this can be either minus 1 or 1. So if it is minus 1, this is 2, and we have 2 minus 2, and that's 0. And if this is -1, this is +2, and of course it can only be larger. So in the last case, we have the exact opposite of the above. In this case, we have that I is not in A, but it is in B. Okay, so you can see it's exactly this is exactly the opposite of this. So of course we get the same thing. It's symmetric in that sense that we are left with chi B instead of chi A. And the same reasoning exactly applies here like it applied in this case. So again, we get that it's larger or equal to 0. So basically we've concluded that when A and B are disjoint, then H is monotone on each edge from x0 to x1, because we looked at what happens when I is not in the intersection. We looked at what happens in the difference between the hx1 and hx0 and showed that it is always larger or equal to 0. So now we're in claim B, where we want to show that when the intersection between A and B is non-empty, then H is 1/8 far from monotone. So let the intersection between A and B be non-empty. So what happens when I is the intersection between A and B? So again, we will subtract h of x0 from h of x1, and we get the following term, and now we will see what happens. So for each x that satisfies chi A of x0 equals chi B of x0 equals 1, we can see that if this equals 1 and this equals 1, these two equal -4 together. They sum to -4, all this term. And this we know already from previously. We know that this is 2, so it tips into the negative. And that means that h of x0 has to be larger than h of x1, which is what's written here. And this violates monotonicity. And now the question is, in order to show that H is 1/8 far from monotone in this case, we want to show how often this condition is satisfied. So the way we will prove this is we'll partition 0, 1, n into 2 to the n-1 pairs with endpoints in the ith direction, just like we have our pair here of x0 and x1. Okay, so just like this pair, we can construct the 2 to the n-1 pairs. So what we will do is we will show that at least one quarter of these pairs satisfy the condition that showed us that there is a violation of the monotonicity. So we will start with the case where A is exactly I. So in this case, chi A of x0 is equal to -1 to the power of xi 0. So what is xi0? For x0, we know that the ith bit is set to 0. And so we have -1 to the power of 0 equals 1. And this is always the case, so it's going to be with probability 1. Now let's look at some j for which j is not I, and it's an A. Then in this case, given x0, we can define x hat 0 to be x0 with the jth bit flipped. So in this case, we know that chi A of x0 equals minus to the chi A of x hat 0. And why is that? Again, because one of them will have, in the power of -1, will have an extra 1. Okay, so one of them will be negative and the other will be positive, and so they will have flipped signs. So in this case, what we can understand is that chi A of x0 will be 1 with probability half in such a case, because every j in 1 through n has probability half of being 1 and probability half of being 0. So this is the same also for chi B of x0. So all this analysis holds also for chi B of x0. And therefore we can conclude that with probability at least half times half equals 4, and why at least? Because we also have this case. But if we, for a second, just think about these cases, then it's with probability half times half equals a quarter. We get that chi A of x0 equals chi B of x0 equals 1. So with probability at least a quarter, we get that these values are the same and equal to 1, which was what caused the violation of monotonicity. So this is what we wanted to answer. We wanted to answer how often this equality, this condition of them being equal to 1, is satisfied. And we just showed that at least 1/4 of these 2 to the n-1 pairs that have endpoints in the ith direction require changing either hx1 or hx0 in order for h to become monotone, in order for the monotonicity requirement not to be violated like we saw before. So therefore we know that 1/8, okay, 1/8 we're transitioning from the pairs to entries, so we know that 1/8 of the 2 to the n entries need to be corrected. So that means that h is 1/8 far from monotone. So now we will prove case number 2, which is this case. So we will do a reduction from set disjointness. So we'll assume without loss of generality that this is a subset of our range, and otherwise we could just map the ith least element of the range to the ith least element of our range, and therefore we can assume this. So in this case, Alice and Bob receive A and B, subsets of 1 through n. And what they do is, again, they build chi-A and chi-B just as we saw before. So the difference here will be that we will be defining a new combining operator psi of chi-A, chi-B that returns h prime. So h prime of x is going to be defined as such. So we have Hamming weights in the middle range. So in this case, it will be exactly h of x. And we will have Hamming weights that are very low. They will be rounded up to this value, which, if you can recall, is the bottom of the range that we saw previously, which is subset of R. And if it is very high, it will be rounded down to the upper end of the range that we saw earlier, included in R. So what Alice and Bob will do, they will run their protocol for C mono with this psi to solve their instance of set disjointness. So we will show claim 4.1, which is that if A and B are disjoint, H prime is monotone, and if A and B intersect, H prime is far from monotone. So this is very similar to what we saw in the previous case. So to prove this, as before, we will fix I to be a subset, included in 1 through n, some index in 1 through n. And for some x, just as we did before, we will have x0 and x1. Again, this is exactly as we set before. So if the intersection of A and B is empty, then we claim that H prime is monotone. How will we show this? So first of all, we notice that H is monotone. This is from case 1, where A intersection with B is empty. Okay, so we know that in this case, H is monotone. And so what we can see is that if the Hamming weight of x0 and the Hamming weight of x1 are both in the middle range, so in the middle range, we saw that H prime of x is equal to H of x. So in this case, we have that H prime of x1 equals H of x1, and H prime of x0 equals H of x0, and we know that H is monotone in this case, on this edge. Then therefore we know that this side is larger or equal to this side, and we still have the monotonicity. Now if x of 0, its Hamming weight, and the Hamming weight of x1 are both in the range of being very low, or both in the range of being very high, then we know in these two ranges that H prime is constant. It gets a constant value. So of course it's trivially monotone if they are both together in one of these ranges. Okay, so the more interesting case is if the Hamming weight of x0 and the Hamming weight of x1 are in different ranges. But in this case, what we should pay attention to is the fact that H prime of x equals H of x for all x that satisfy the middle range. And what is H of x? H of x is something that it's included in this range between the lowest value and the highest value. And keeping that in mind, what we can see is that for every x, y, and z for which the Hamming weight is going to be such that its value, its H prime, is going to be rounded up to the lowest part of our range, and z has Hamming weight that's going to be rounded down to the highest part of our range, and we have for y, it's going to just be somewhere within that range, because we know that for y, H prime of y in the middle range equals hy. Then of course we will have this relationship where H prime of x is less or equal to H prime of y, and which is less or equal to h prime of z. Okay, so we finished showing that if the intersection between A and B is empty, then h prime is monotone. So now we will move on to the second part of the claim, which is the intersection of A and B is not empty. Then we want to show that h prime is 1/16 far from monotone. So what we know is that in this case, h is 1/8 far from monotone. We saw this in case 1 with A intersection with B not being empty. So we know this. So now we set x to be an element in 0, 1, n, some uniform random string. So now we will look at the probability that h prime of x does not equal h of x, and this will help us later on with a triangle inequality to reach what we wanted to prove. So this probability is the same as the probability that x falls outside the middle range. And why is that? Because we saw that when x falls outside the middle range, it does not equal, h prime does not equal h, and when it does fall inside the middle range, h prime equals h. So looking at the probability that x falls outside the middle range, we can see it by the Chernoff bound, and this is exactly the statement of x falling outside the middle range. So by the Chernoff bound, we get that this probability is less than 1/16. And so the probability that h prime of x does not equal h of x is less than 1/16. So let's assume by contradiction that h prime is not 1/16 far from monotone. So we'll denote by h tilde the closest monotone function to h prime. Now, by the triangle inequality, and h prime being at most 1/16 far from h, which is what we just saw in the previous slide, what do we get? We get the following. We get that the probability of hx not being equal to h tilde of x is less or equal to the probability of hx not being equal to h prime of x plus the probability of h prime of x not being equal to h tilde of x. And this is by the triangle inequality. So what do we know? We know from the previous slide that this is less than 1/16. We just saw that. And this, by our assumption, is also less than 1/16. Okay, we assumed this, so we have this is less than 1/16. So in total, we get that this sum is less than twice 1/16, which is less than 1/8. And this cannot be because we know that h is 1/8 far from monotone. So we get a contradiction. So we still need to handle case number 3 for this range size. So what we will do is very simple. We will reduce from the previous case. So we will set A to be an optimal algorithm for testing monotonicity for functions f from 0, 1, n to r. So before we use A to create an algorithm for the case number 2 scenario, what we will do is we will set m to be the largest integer that satisfies the range requirements that we saw in case 2. And then what we will do is we'll use A to create an algorithm A prime for functions g from 0, 1, m to r. And we will do that using the following claim. So claim 4.2 will help us with this case. So this claim states that given a function g from 0, 1, m to r, there exists a function h from 0, 1, n to r with the following properties. If g is monotone, then h is monotone. If g is epsilon far from monotone, then h is epsilon far from monotone. And for every x in 0, 1, n, the value of hx can be determined with one query only to g. So to prove claim 4.2 before we can use it in our reduction, the way we'll prove it is we will construct h from g using padding. So we will define h of xy to be g of x for strings, x in 0, 1, m. Okay, the size of the string is m bits, and y 0, 1, n is 0, 1 n minus m, meaning the remaining will be y. So conditions 1 and 3 are obviously satisfied. If g is monotone, then of course h is monotone. And for every x in 0, 1, n, the value of h of x can be determined with one query to g, of course. This is obvious. Okay, so for 2 we need to work a bit harder. So we will assume by contradiction that h is not epsilon far from monotone. So let h tilde be the closest monotone function to h. So in this case, we see that the probability of over x and y of h tilde xy not being equal to h of xy is less than epsilon, again because h tilde is the closest monotone function to h, and we're assuming that h is not epsilon far from monotone. So if this holds, then there has to be a y tilde in 0, 1, n minus m, such that the probability over x of h tilde xy tilde not being equal to h xy tilde is less than epsilon. Again, because if this doesn't hold for some y, then this cannot be true. So we will define g tilde from 0, 1, m to r as being g tilde equal to h tilde x of y tilde, meaning the definition of g tilde is exactly h tilde x y tilde. So of course g tilde is monotone. Why? Because h tilde is monotone by definition, and g tilde is defined by h tilde. But what we can see is that the probability over x of g tilde x not being equal to g of x, it's equal to this statement. Now why is that? G tilde of x is, we just defined that, so we have h tilde of x y tilde and g of x, but when we look at the probability over x holding y tilde fixed, then we get that g of x is h of x y tilde as we've defined earlier, and so we get this probability. So this equals this, and of course we know, again, because h tilde is the closest monotone function to h, and h is assumed to not be epsilon far from monotone, as we wrote here, we know that this has to be less than epsilon. But this being less than epsilon contradicts g being epsilon far from monotone, because we know that g is epsilon far from monotone. So we are now ready to construct a prime. So given input g from 0, 1, m to r, this is the input for the case 2 that we are reducing from, let h be the function guaranteed by claim 4.2. So what a prime will do, a prime will run a on h and accept if and only if a accepts h. Now by claim 4.2, the correctness of a prime immediately follows from the correctness of a. Why? Because if g is monotone, we saw that h is monotone by claim 4.2.1. And if g is epsilon far from monotone, then we saw that h is epsilon far from monotone as well by claim 4.2.2. So therefore, the correctness of a prime immediately follows from the correctness of a. So now we just need to discuss the complexity analysis for a. So we can see that a prime uses one query per query of a. And why is that? That's because of claim 4.23. h of x can be determined with one query to g. This is for claim 4.23. However, we know that testing g requires omega of m queries. And why is that? Because we know that g satisfies the conditions of case 2 that we have proven earlier using a reduction from set disjointness. So testing g requires omega of m queries. In terms of r, omega of m is omega of the size of the range squared. Why is that? Because of this relationship. So as we just said earlier, A is an optimal monotonicity tester that uses the same number of queries as A prime, and therefore this alongside the complexity of testing G gives us that testing some f from 0, 1, n to r for monotonicity requires omega of m, which is in r terms of r, omega of size of r squared queries, for the case where the size of the range is little o of square root of n. So we will now move on to testing submodularity. So first we will define what that is. So the function f from 0, 1, n to the real numbers is submodular if for every x, y in 0, 1, n, fx plus fy is larger or equal to f of x or y plus f of x and y. And just to be clear on the notation, so if we look at one index, some index I, so x or y on this index means that we are taking the maximum between the two on this index, and x and y for the index I is the minimum between the two on this index. So we will use the theorem 1.6 that we just saw, along with a lemma that's from the literature, to show that testing submodularity requires omega of n queries. So we will present the lemma, lemma 4.1, which we will be using. Again, this is a lemma from the literature. So given the function f from 0, 1, n to the real numbers, there exists a function g from 0, 1, n plus 1 to the real numbers with the following properties. The first property is that if f is monotone, then g is submodular. The second is if f is epsilon far from monotone, then g is epsilon divided by 2 far from submodular. And 3, for each x in 0, 1, n plus 1, the value of g of x can be determined with 2 queries to f. So we will be using this in our proof. So here is theorem 1.7 that we will be proving. So the theorem is very simple, testing f from 0, 1, n to the real numbers for submodularity requires omega of n queries. So the proof for theorem 1.7 is actually very simple. So we will take a function f from 0, 1, n minus 1 to the real numbers to be a function that we want to test for monotonicity. And we will define g from 0, 1, n to r to the real numbers be the corresponding function guaranteed by lemma 4.3. So in order to test f for monotonicity, what we can do is we can simulate a submodularity test at t on g. And why is that? This is by 1 and 2 that we just saw in lemma 4.3. And of course, if t makes q queries, then by lemma 4.3 number 3, we can see that the monotonicity tester makes twice as many queries, 2 q queries. And now if we just take theorem 1.6 that we just recently saw, then testing monotonicity, we know from this theorem, it requires omega n queries. So therefore, very simple, submodularity testing also requires omega of n queries. So now we will move on to testing concise representations. So first we will define what a decision tree is. We'll give a formal definition, and later we will also show a definition of what a branching program is. So now we will look at decision trees. So a decision tree is a directed binary tree where each internal node is labeled from 1 through n, okay, just as we can see here, an illustration of one of these. Each internal node has 2 outgoing edges, one labeled with 0 and another with 1. And each leaf is a value in 0 or 1. Okay, so if we had a leaf here, we would get 0 or 1 in these leaves. So the decision tree D is said to compute function f from 0, 1, n to 0, 1 if, for every x in 0, 1, n, the path defined in D by querying xi's value at each internal node labeled with I. So if we were in xn or labeled with n, so we would be querying xn. And following the corresponding edge of what the value gives us, so if xn gave us 0, we would follow this edge. It leads to a leaf with the value fx. So that's what we say when we say that D computes function f. The size of a decision tree is simply its total number of leaves. So we will now define a branching program. So this is a directed acyclic graph with 2 sync nodes labeled 0 and 1. All non-sync nodes have out degree 2, and each one of them has a label from 1 through till n. The 2 edges leaving a node are labeled 0 and 1. So as we saw earlier, we have edges with 0 and 1. And the branching program P is set to compute function f from 0, 1, n to 0, 1 if every x in 0, 1, n defines a path in P that leads to the sync labeled with f of x. And the size of a branching program is its total number of nodes. So we will now look at theorem 1.8. So what we want to prove is that at least omega of minimum s and n minus s queries are required in order to test size 2 to the s decision trees and size s branching programs. And the proof is going to be very similar to the proof for 1.1 using a reduction from set disjointness. So before we prove theorem 1.8, we have to prove two lemmas that we will be using. So lemma 5.3 states the following. So we fix s at least 1 and alpha between 0 and 1, non-inclusive. And we will set f from 0, 1, n to 0, 1 to be some s-linear function. Then in this case, the theorem states that f can be computed by a decision tree, which we will denote with dt, of size 2 to the s. And also f is 1 minus alpha divided by 2 far from all functions computable by a decision tree of size at most alpha 2 to the s. So now we will prove lemma 5.3. So first we see that we can compute a function f from x to the s variables that it's s-linear with. So we have xi1 XOR with xi2 and so on until we reach XOR xis. And we can do so using a decision tree of size 2 to the s by creating a complete tree of depth s. How? So each node at level j is going to query xij, and this query will determine which edge to take next. So we will get from this query either 0, 1, or 1, and we will follow that edge to the next level. So this tree has 2 to the s leaves, where the value of each leaf is set appropriately so that upon reaching the leaf, when we reach the leaf after following these queries, the edges according to these queries, we have computed fx exactly. Okay, so we can see that we can compute this s-linear function using a decision tree of size 2 to the s, as we defined. So we will take another decision tree t, okay, this is another decision tree, of size at most alpha times 2 to the s, and this decision tree computes some of the function g from 0, 1, n to 0, 1. Now what we want to show is we want to show that the probability of fx not being equal to g of x is at least 1 minus alpha divided by 2, where this probability is taken over the uniform distribution of x in 0, 1, n. So first, some quick definitions. So for each leaf L of t, we will define depth L. This will denote the number of unique variables that are queried by the nodes in the path from the root of t to L, to the leaf L. And RL, which is a subset of 0, 1 to n, is going to be the set of inputs, the set of x's, the set of inputs in 0, 1, n, that define a path in this tree T that reaches the leaf L. And notice that this induces a partition on x, because more than one x can reach this same leaf. Also, we will define B to be the union of the sets RL for all leaves in T that have depth less than s. And finally, we have M, capital M, it's just the maximum depth of a leaf in T. So we're interested in the probability that fx does not equal g of x. And this is larger or equal to the probability that fx does not equal g of x, and we're in the case where x is in B. Okay, so this transition is because this is more limiting than this. So of course it will be this will be smaller or equal to this. And this is equal to the probability that x is in B times by the probability that fx does not equal g of x, given that x is in B, and this is simply the transition to the conditional probability. Okay, so the first thing we want to do is to show what probability of x being in B is. Now remember that x being in B means that x reaches L at depth less than s, okay? It's very similar to what's written here, but less than s. So what we can do is look at the probability that x reaches L at depth at least s. So before we do this, we can just notice that the probability that x reaches leaf L equals 2 to the minus depth of L. And why is that? Because every time on the path to L, we have to choose an edge, which is either going to be 0 or 1, and the probability of it being 0 is half, and the probability of it being 1 is half. So this is half to the power of depth of L. Now from the union bound, if we want to see what this probability is, we can get that it's less than or equal to the sum of the probabilities reaching at least depth, reaching depth s, reaching depth s plus 1, and so on until we reach depth m. Okay, this is by the union bound, this relationship. And then if we want to get an upper bound for this sum of probabilities, we can observe that we have m minus s plus 1 terms, and we can take the highest probability of all of these, which is this, the probability that x reaches L at depth s. Of course, we can see this is the highest one because anything deeper than that has a lower probability. So if we replace all of these summation terms with the probability that x reaches L at depth s, we get that it's smaller or equal to this value, this term. And of course, this term is upper bounded by the number of total leaves that we have, which is alpha times 2 to the s leaves. Okay, this cannot be more than the number of leaves that we have. And of course, the probability that x reaches L at depth s is 2 to the minus s, as we saw here. In total, we get that this is alpha. So this probability is less or equal to alpha. And therefore, we get that the probability of x being in B equals 1 minus the probability that x reaches L at depth at least s. Okay, this is less than s, and this is at least s. And this equals 1 minus alpha. So now we will compute the other term that we had, which is probability of fx not equal g of x, given that we are looking at x in B. So let L in T be a leaf of depth at most s minus 1. So there has to exist some index I in those meaningful s-linear indices that we have. So we have I1 until is. Okay, so one of these is not queried on the path to L. Why? Because it is at most depth s minus 1. So there has to be such an index. So what we can do is we can partition RL into pairs x and xi. And what is x and xi? X is basically like xi, except on coordinate I. So they just differ on the coordinate I. If one is 0, the other is 1, and vice versa. So for each of these pairs, what do we have? We have that fx does not equal f of xi. And why is that? Because we know that f is s-linear, and I is in its meaningful s variables. So if they differ on the ith bit, it can't be that they are equal. Okay, so therefore, what we can see is that the probability that fx does not equal g of x, given that x is in RL, okay, it's one of the inputs that reach the leaf L, this will be equal to half. Why is that? G of x can get values that is either 0 or 1, and the value that it will get is regardless of the ith bit, because we just saw that the ith variable is not going to be queried on the path to L. Now, fx depends on the ith bit, and specifically in half the cases, because we're in the uniform distribution, in half the cases fx equals 0, and in the other half fx equals 1. And therefore, we get that the probability will be half. And if we don't limit ourselves just to the specific leaf L, but rather look at all those leaves that can reach up to depth s minus 1 inclusive, so we get that the probability for fx not equal g of x, given x is in B, equals half. So now we are finally ready to combine all of this together and compute this original term that we wanted, which is the probability that fx is not equal g of x, which we broke down into the probability of x being in B and the probability of fx not equal gx given x in B, and combining this with what we just saw. So we saw that probability of x in B is 1 minus alpha, and the probability of this statement is half. So in total, we get 1 minus alpha divided by 2. So this proves what we wanted from Lemma 5.3. So as you recall, before proving theorem 1.8 that we want to prove, we need to prove two lemmas. So we just saw Lemma 5.3, so we will now prove Lemma 5.4. So what does Lemma 5.4 state? It states the following: let P be the class of all Boolean functions computable by branching programs of size 2s. Then every s linear function is in P, and every s plus 2 linear function is 1/6 far from p. So we will prove this. Okay, so we will first show that every s linear function is in P. So this is very straightforward, very simple. We can create a branching program of width 2, where every level except for the start node has 2 nodes, of course. And this branching program queries xi1 at the start node, and then it queries xij at the 2 nodes on level j, that is, of course, not the start node, all the way until level s included. And so we just rearrange the edges so that the left without loss of generality, the left node at level j is reached when the XOR of all these variables leading up to j, not including j, equals 0. So this guarantees that we get to the 0 sync node if the XOR is 0. So this specific branching program has size 2s minus 1. 2 on each of the s levels that correspond to the s variables, except for the start node. Therefore, we have minus 1. So, of course, this is computable by a size 2s branching program. So now we will show that every s plus 2 linear function is 1/6 far from P. So let P be a branching program of size 2s. So we should notice first that if there is some variable in H that is not in P, then what we will get is that H and P are half far. Why? Because then for every input, we could flip the variable, the missing variable's value, to change the value of H, but this would not affect the value of P. So obviously, if it is half far, then it is definitely 1/6 far, and so moving forward, we will now assume that every variable in H must also be in P. So P has size 2s, and therefore, along with the assumption that we just said, where every variable in H is in P, then we can see that at least 2 variables in H, which we will denote with x1 and x2, have to be queried only once in P. Otherwise, for example, if we are querying s out of s plus 2 twice, then we already cover the 2s nodes. So let U1 and U2 be the corresponding nodes in P, corresponding to x1 and x2. And note that P is DAG, so we can assume without loss of generality that U1 will not be visited after U2. And now we will take x1, x and x1 from 0, 1, n to be as such. So x is from the random uniform distribution over 0, 1, n, and x1 will just be identical to x, except that we flip the bit in x1, the bit in variable x1. Now, note that both x and x1 are generated uniformly. So first we will look at the option that the path for x reaches u2 with some probability less than 2/3, and later we will see the opposite case. So in this case, with probability at least 1/3, flipping x2 changes the value of h, okay, it's one of its s plus 2 variables, but it doesn't change the value of p. And why is that? Because in this assumption, we're looking at the case where x does not reach u2. Okay, so p will not be querying x2. So therefore, if this is the case, then we can see that the probability that p's output for x will not be equal to h of x is going to be larger or equal to 1/3 times by half. Why 1/3? 1/3 because we're in this case where we're not reaching u2. And half because we don't know which of the bits will be placed in x2. Okay, so it depends on which value x2 got, if it does not allow to match to h of x. And so this gives us 1/6. So now in the other case, if the random path for x reaches u2 with probability at least 2/3, what do we get? We get that also the random path generated by x1 reaches u2 with probability at least 2/3. It's completely symmetric to x. We did not set in stone any bit here, so it's just the flipped scenario for x, and so they are randomly uniformly chosen, as we mentioned before, and so they have the same probability to reach u2. So we will denote with A the event where x reaches u2, and with B the event that x1 reaches u2. And so what we can see is that the probability of event A occurring or event B occurring is equal to the probability of A occurring plus B occurring minus the probability of both of them occurring. And this is larger or equal to 2/3 plus 2/3 minus the probability of A and B occurring together. And these 2/3, again, they come from the fact that the x reaches U2 with probability 2/3, and so does x1 reach U2 with probability 2/3. So what does this mean for the probability of A and B together? So this has to mean that the probability of A and B occurring, both of them reaching U2, has to be at least 1/3. Why? Otherwise, if that's not the case, then we have from the previous slide, we just copy pasted what we had from the previous slide. We have that the probability of A not being, A or B is larger or equal, as we said before, but this term is larger than 2/3 plus 2/3 minus 1/3. Again, because this is going to be less than, in this case, in the otherwise case, this is going to be less than 1/3. And so this cannot be, of course, because this sums to 1, and it cannot be that the probability of A or B happening is larger than 1. It would not be a probability. So x and x1, they only differ on this variable, x1, but both of them reached U2. Now, we assumed without loss of generality that they reach U2 after U1, and after that, after reaching U2, they cannot reach back U1 because it's DAG, directed acyclic. So that means that their paths lead to the same terminal in P, okay, because they both reached U2, and from then on, they are completely identical. So they reach the same terminal in P, despite the fact that h of x is not equal to h of x1. And again, this is because x1 is one of the variables in the s plus 2 variables in h that are meaningful. So therefore, again, we have that the probability of P's output for x, let's assume here x without loss of generality, is not equal to h of x, is larger or equal to 1/3, 1/3 for being in the scenario where both reached U2, times by half for being in the scenario where we happen to choose x for which h of x does not equal the terminal that they both reached. Again, this is without loss of generality. It could also be x1. And this is larger or equal to 1/6. So now we move on to theorem 1.8 finally, which uses both of these lemmas that we just saw. So the theorem states that at least omega of minimum s n minus s queries are required in order to test size 2 to the s decision trees and size s branching programs. And we mentioned earlier we will be using a reduction from set disjointness, and we will now also be using these two lemmas. So we will now prove theorem 1.8. So we define two communication games, this one, and they will be defined as follows. So Alice and Bob receive f from 0, 1n to 0, 1. And their goal is to test whether h, which is f XOR g, is computable by size 2s decision trees. Okay, this is going to be the notation that we will use for this game, or size s branching programs for this notation. Okay. So as always, we will be using Lemma 2.4 and something that we have already proven a lower bound for in the communication complexity world. So this is going to be the S-balanced disjoint. So we have the following relations from these two lemmas. These two are from Lemma 2.4 and this is Lemma 2.6. So for example, we have twice the query complexity of size 2 to the s decision trees is at least as complex or costly as the minimum communication cost for the corresponding communication game we just defined for decision trees, 2 to the s size decision trees. So it remains to show, to link somehow between this communication complexity and these as well. So we basically want to show these relationships that they hold, and then we get lower bounds for these two. So Alice and Bob receive as input to S-balanced disjoint the following two sets, A and B, A for Alice, B for Bob, from 1 to n, and the sizes are as we would expect for the input for S-balanced disjoint. And they each construct a parity function, so parity A and parity B from 0, 1, and to 0, 1. And so what we can see is that when the size of the intersection is 1, and it has to be either 1 or 0 because it's guaranteed from the S-balanced disjoint problem setup. So when it is 1, we have H equals parity A XOR parity B. And this we've already seen equals the parity of the symmetric difference between A and B. And so in this case, if the intersection is 1, we just get that it is S-linear. Okay, this is because of the sizes that they got. So if they intersect again, it is S-linear. And we saw that S-linear can be computed by size 2 to the S decision trees and size S branching programs. Now, what happens when the intersection is empty? So in this case, again, we've also seen this in the past. So H is S plus 2 linear and very simple directly because of the sizes that they have and the fact that they don't intersect on any item, any index. So by lemma 5.3, when H is S plus 2 linear, we will now see that it is 3/8 far from functions computable by size 2 to the S decision trees. Why is that? Because we can see 2 to the S can be written as 1/4 2 to the S plus 2. And so we can say that alpha equals 1/4. And then we can look at lemma 5.3. Instead of for S linear functions, we look at S plus 2 linear functions. And so in that case, lemma 5.3 says that H is 3/8 far from functions computable by size 2 to the S decision trees. Again, to show you why. So we can see here, again, if we look instead of S linear, S plus 2 linear, then we can see that it is 1 minus alpha quarter, divided by 2, far from all functions computable by decision tree of size at most alpha 2 to the S plus 2. And in this case, we saw that alpha 2 to the S plus 2 is actually 2 to the S. So that's how we got this relationship. Now we will see that by lemma 5.4, when H is S plus 2 linear, it is 1/6 far from functions computable by size S branching programs. This is actually pretty straightforward. Again, just to remind you, we can see that this relationship is derived exactly from this statement. Every S linear function is in P, and every S plus 2 linear function, as our H is 1/6 far from P. So just to conclude this case is, again, when A and B are disjoint, if you remember from the earlier slide. So in this case, we saw that H is S plus 2 linear. And so in this whole slide, we saw that when H is S plus 2 linear, it is far from functions computable by size 2 to the S decision trees. And it's also far from functions computable by size S branching programs. And so therefore, in total, we know that Alice and Bob can solve their S-balanced disjoint problem using protocols for these corresponding communication games. Again, because if they do have an intersection which equals size 1, then we know that it is S linear, and when they don't have an intersection, when they are disjoint, we know that it is S plus 2 linear, and so therefore this is valid. Okay, so now we will be talking about testing hunters. So just to give motivation for the next few slides. So we know that testing k-hunters is omega of k. This is a known previous lower bound. And Fisher et al. In 2004 asked whether it might be easier to test k-hunters in a relaxed sort of formulation. And specifically, they asked maybe it will be cheaper if we only reject functions that are far from k plus 2 hunters for some t larger than 0. Will it be cheaper than omega of k? And in the literature, in 2004, these two authors gave a lower bound of omega of k divided by t. But this is not sufficiently strong to answer Fisher et al.'s question for any t that is little omega of 1. And specifically in the next few slides, we will see that it is actually asymptotically similar to testing k-hunters, which is omega of k. And so just to understand why this is not sufficiently strong, imagine, for example, if t equals square root of k, so we end up with omega of square root of k. And here we will see that it is omega of k. So as I mentioned, the next theorem is going to show that for any t less or equal to big O of square root of k, distinguishing k hunters from functions far from k plus t hunters will require asymptotically the same query complexity as the standard k hunter testing problem. So more formally, we have theorem 1.9. We will fix k less or equal to n divided by 2 and t larger than 0. So any algorithm that accepts k hunters and rejects functions far from k plus t minus 2 hunters with high probability must make omega of the minimum between k divided by t squared and k queries. And we will prove this via a reduction from the extended gap Hamming distance that we denoted as EGHD. So just to remind you what the extended gap Hamming distance is, so it's the extended version of the gap Hamming distance. We have n, k, and t. Alice and Bob are given n bit strings, x and y respectively. They are equal in their Hamming weight, which equals k, it's this k. And their goal is to distinguish between the case of the Hamming distance between x and y being at least k plus t, and the Hamming distance being less or equal to k minus t. And we saw this formulation where star means that it can return 1 or 0 if it's not one of these cases that we just mentioned here. So I will also remind you of Lemma 2.10 that we saw for the EGHD problem, which stated that for every kt less or equal to n divided by 2, we had that the minimum communication cost of EGHD nkt is omega of this statement, which we are looking to obtain. So first thing we notice is that if t equals omega of k, then there is nothing to prove. And why? Because omega of k divided by t squared will be trivial. This is going to be what comes out of the minimum. The other term is k. So of course, if t is omega of k, we're going to get this trivial lower bound, omega of 1. So we will assume that t equals little o of k. So what we will do is we'll define this communication game. We'll denote by this the communication game where Alice and Bob receive f and g for Alice and Bob from 0, 1, n to 0, 1. And their goal is to determine whether h, which is the XOR of f and g, is a k hunter or whether it is far from k plus t minus 2 hunters. So we know that by Lemma 2.4, we have the relationship between the query complexity of this property that we defined in the communication game and the corresponding communication complexity for this communication game we just defined. Okay, this is from Lemma 2.4, we keep seeing this. And from Lemma 2.10, which I just reminded you of for EGHD's lower bound, we get the following with these parameters. Okay, if we change k to k plus t divided by 2 and t to, we changed to t divided by 2, we still get this same lower bound, and this is because k plus t divided by 2 is theta of k. So all we need to show in order to get a lower bound for the query complexity, we just need to link between these two and actually show that, that this relationship holds. And then we get the lower bound that we want for this property. We will get that it is omega of this expression. So we will now show this using our reduction from EGHD. So let x and y be the input to EGHD for Alice and Bob respectively. So what they do is they construct the parity functions using these sets. So Alice has parity A from 0, 1, n to 0, 1 with indices I such that xi got 1. And Bob does something very similar. He constructs the parity function on the set B, again also like Alice did with indices such that yi equals 1. And then what we can see is that H is defined to be the parity A XOR parity B, which is, we've already seen several times now, this is equivalent to the parity of the symmetric difference between A and B. And of course, parity of the symmetric difference between A and B is linear in the size of the symmetric difference between A and B. So the first thing we should notice is that the Hamming distance between x and y equals the symmetric difference between A and B, the size of the symmetric difference between A and B. And this is because the Hamming distance is the number of indices that they differ on, and of course, if they differ on one of the indices, it will be included in this symmetric difference. So what we need to do now is look at the two cases for the extended gap Hamming distance. One is for this relationship when the Hamming distance is less or equal to this value, and the other is when it is larger or equal to this value, and see what we get. So in this case, when the Hamming distance between x and y is less or equal to this value, which equals k, then what we get is that h is a linear, it's a parity function in less or equal to k variables, and therefore, of course, it is a k-Junta in this case. Now, what happens in the other case? In the other case, we get that it is larger or equal to this value, meaning it's larger or equal to k plus t. And we then go to proposition 3.42, which I will now present again, just to remind you, where we can see that h is half far from k plus 2 t minus 2 Juntas. Okay, so we will now see this proposition. Remember that in our case we have k plus 2 versus k plus t minus 2. So here in this proposition we are interested in number 2. We saw this earlier, so we can see that if f is a k plus 2 linear function with these conditions, then it is half far from k Juntas. In our case, we have k plus t, and not k plus 2, we have k plus t. And so to get this relationship, we just need to deduct 2. It's just the same. So we get k plus t minus 2. So it's half far from k plus t minus 2 Juntas. So this is what we got here. So now we can see that Alice and Bob can run their protocol for this communication game in order to solve their instance for EGHD. Again, the communication game will test h for being k-Junta, in which case we're in this scenario, or if h is half far from k plus t minus 2 Juntas. So then we get the relationship that we were looking to obtain from this reduction, and so we complete the proof. So now we will move on to testers with one-sided error. So we're going to be talking about specifically testing decision trees now. And we showed that omega log s queries are required in order to test if a function can be represented by a Boolean decision tree without most s nodes. We showed that earlier. However, we will now see that for testers with one-sided error, we get an exponentially larger lower bound. So now we will prove another theorem, theorem 1.11, which states that at least omega n queries are required in order to test size s decision trees with one-sided error. And we will prove this via a reduction from the gap equality problem on s-bit strings. So in order to prove the theorem, we will set s to be equal to 2 to the n minus 1 for some n larger or equal 5. And we will define the following communication game with this notation, which says that Alice and Bob receive f and g from 0, 1, n to 0, 1. And the goal in this communication game is to test whether h, which is the XOR of f and g, is computable by a decision tree of size s. So by Lemma 2.4, which we keep seeing, we have the relationship between the query complexity of the one-sided case and the communication complexity of the one-sided case. And according to Lemma 2.7, we've also seen the lower bound for GEQ for the one-sided case. With these parameters, we get that it is omega of s. So if we want to obtain the lower bound for the query complexity, we need to link between these two, and specifically, we need to show this relationship. And we will do that through a reduction from GEQS with s divided by 8 to our communication problem. So for the GEQ problem with s and s divided by 8, the input that Alice and Bob receive is each one receives a binary string of size s, okay, from 0, 1, s. And their output is they need to determine if a equals b, or if the Hamming distance between a and b is s divided by 8. So how will they solve this? We will fix the bijection between the vectors x in 0, 1, n that have even parity and the indices 1 through s. So notice that this defines an indexing of the bits of a and b, again because x, in case it's even parity, maps us to a specific index in a, and the same for b. So Alice and Bob will build the following functions, f and g, from 0, 1, n to 0, 1 as follows. So f of x equals to a of x when the parity of x equals 0. Remember that in this case x gives us a specific index to look at, so we get the value at that index, and 0 when parity x equals 1. And Bob does something slightly different. In the case when parity x equals 0, we get b of x. Again, x maps us to a specific index in b, and so we get back that the value at that index. But when parity x equals 1, we get 1. So what they will do is they will test whether f XOR g, that we just defined, can be represented by a decision tree of size at most 15 divided by 16 times 2 to the n. And if it can, they answer that the Hamming distance between a and b equals s divided by 8. So we will now prove that this is correct. So for any x in 0, 1, n with even parity, we just saw that in the case of even parity, each one of Alice and Bob, each one of their functions for x gives us back the value at the index that matches x. Okay, and so therefore we have ax XOR b of x in this case. And for any x in 0, 1, n with parity equals 1, what we saw is that Alice returns 0 and Bob returns 1 in this case, and so the XOR of f and g for x equals 1. So now what we can notice is that a equals b means that the function f XOR g is exactly the parity function. And why is that? Very easy to see. Parity of x equals 1 means that we're in this case, and so we always return 1. Okay, so of course it's going to be identical in this scenario. Now we need to show that when parity of x equals 0, we always get 0. And then in this case, if this is the case, then we indeed get the parity function back. So we just need to show this case. So very simple, ax XOR b of x in the case where a equals b is always 0, because again, either this is 1 or this is 1, or this is 0 and this is 0 because they are equal, and so we always get 0 in this case. So parity x equals 0 gives us 0, parity x equals 1 gives us 1, and so we are indeed getting the parity function in the case where they are equal. So now let's continue with this case where a equals b, where we just saw that f XOR g is exactly the parity function. So how large a decision tree is required in order to compute parity exactly over n variables, meaning it's n linear? So by Lemma 5.3, which we recently saw, we know that an n linear function can be computed by a size 2 to the n decision tree. We also know by this same lemma that a function computable by a decision tree of size 2 to the n is 1 minus alpha, we have some alpha here, 1 minus alpha divided by 2, far from all functions computable by size alpha 2 to the n decision tree. Notice that we, instead of alpha, we put 15 divided by 16 in these two cases, and we get that a function computable by a decision tree of size 2 to the n is 1 over 32 far from all functions computable by size 15 divided by 16 2 to the n decision trees. So before we move on to the next case, to conclude the case where A equals B, we know that we get a parity function, f XOR G is parity, and we know that a parity computing decision tree is 1 over 32 far from decision trees of size at most 15 divided by 16 to the n. So now we look at the case where the Hamming distance between A and B is s over 8. So in this case, we can compute f XOR G using a complete decision tree by simply querying xi at each node at level I. Okay, so we get the value xi at every node for level I. So when we finish level n, we can obtain the value that matches the index provided by x for A and the value that matches the index provided by x for B. So this tree has 2 to the n leaves, but some of them are redundant. So in order to see this, we can look at every x where ax is not equal b of x. So in this case, we have that f XOR g of x equals 1. Why? Because we saw by the definition earlier that for parity x equals 1, we always get 1, we always get this. And we also saw that for parity x equals 0, for even parity, we have ax XOR b of x. Okay, this would be ax XOR b of x, but in this case they are not equal, so we get 1. So in any case, we get 1. We have 2 sibling leaves identical to 1. So for each such x, we can eliminate one of these leaves. So how many of these cases do we have? So the Hamming distance between A and B equals s divided by 8. So that means that 1/8 of the indices, okay, remember that x for even parity maps to 1 through s, these are the indices. So 1/8 of these indices is actually causing this redundancy. And that is exactly the 1/8 of the x's that have even parity. So what we can do is we remove 1/8 of these even parity leaves, okay, 1/8 of these cases. And so the number of remaining leaves that we are left with is what we started with, 2 to the n, minus looking only at the even parity leaves divided by 8. So 1/8 of the even parity leaves. Okay, this is just divided by 2 for the even parity. And this is less than 15 divided by 16 times 2 to the n. So just to conclude, we've seen that for this case of gap equality, f XOR g is computable by a decision tree of size at most 15 divided by 16 to the n. And when this is the case for gap equality, then f XOR g is 132 far from such decision trees computable by the same size. So that means that Alice and Bob can indeed use their protocol, which we denoted as this, in order to test whether f XOR g can be represented by a decision tree of size at most 15 divided by 16 to the n in order to solve that gap equality instance, which is what we set out to show. So now we will continue with testers with one-sided error, and this time it's going to be signed k majorities. So first we will provide a definition. So first of all, a signed majority function f from -1, 1, and to -1, 1 is a majority function with some variables that are negated. So we've got fx equals sine of wx, where w is of this form, it's taken from -1, 1, n. Now, if w is taken from -1, 0, 1, n, and exactly k of the wi's are non-zero, so we say it is a signed k majority. Now notice that this means that a signed majority function is also a signed n majority, okay, because it has -1, 1 for all of its n variables. So before we move on to the theorem for signed k majorities, we will prove Lemma 6.1, which we will be using. So Lemma 6.1 states that for every alpha, every positive alpha, there exists a k0 in the natural numbers and epsilon, a positive epsilon, such that for every k at least k0 and k prime at least 1 plus alpha k, all signed k prime majorities are epsilon far from signed k majorities. So before we can prove the lemma, we need to look at the Berry-Esseen theorem, which we will be using to prove this lemma. So let L of x be equal to C1x1 plus and so on, Cn plus Cnxn, be a linear form over the random bits xi in -1, 1. Now we assume that the absolute value of Ci, each one of these like coefficients, is less or equal to tau for all I. So all of the coefficients are less or equal to tau. And we set sigma to be the square root of the sum of the squared coefficients. And ft is the notation for the cumulative distribution function of Lx divided by sigma. So formally, we write the following. So this theorem is actually a version of the central limit theorem that has error bounds. And basically what it states this relationship between the cumulative distribution function f that we just defined and the standard Gaussian cumulative distribution function. Specifically, phi is it denotes the CDF, the cumulative distribution function of x, which we will denote to be a standard Gaussian random variable. So we get this upper bound. And specifically, if we look at some interval of the real numbers, then we get the following relationship. Once again, we can see Lx divided by sigma again that we saw in the previous slide, and x, the standard Gaussian random variable. And this is very similar to what's written here, where C1 is an absolute constant. So now we are ready to prove lemma 6.1. So f will be a signed k majority, g will be a signed k prime majority, and we can notice that f and g have a minimum distance when they have the same sign pattern on the common variables that they share. So we will assume, for simplicity, without loss of generality, that the f of x and g of x are the corresponding sign functions of the first k variables for f and the first k prime variables for g. Again, this is without loss of generality. It's just for our convenience. So to simplify further, we will denote as s of x to be the sum of xi, from I from 1 through k, okay, the first k variables that we saw just now. And t of x will be defined to be the sum of the remaining variables between k plus 1 inclusive and k prime. So recall that k prime is at least as large as 1 plus alpha k, and we have alpha larger than 0, so we are certain to have at least one more variable here. So if we look at this, so we have f of x equals the sign of s of x, simply from the definition, and g of x is the sign of sx plus the remaining variables that we still need to include to get g of x, which is s of x plus t of x. So for any t larger than 0 in the reals, we have that the probability, of course, over x, that fx is not equal g of x, this is what we're interested in, is larger or equal to the probability of sx being in the interval from 0 until t non-inclusive, and t of x less than minus t. Basically, why is this larger or equal to this? So we can see the explanation here. Fx is, in this case, non-negative. Remember, fx is the sign of s of x. So it is non-negative in this case. And g of x, which is the sum of t of x and s of x, will be tipped to the negative because t of x is less than minus t. Okay, so if this can be at most t and what we are adding to it is even smaller than minus t, we will tip into the negatives. Okay, so and this is just one option for them to be different from one another. So we have that the relationship is larger or equal to this scenario. And what does this equal? This equals the probability of s of x being in this interval times by the probability that t of x is less than minus t. And why is that? This is written here because s and t are simply functions on disjoint sets of variables. We just saw that f is for the first first k variables, and g is for the first k prime variables, and we know that t is running from k plus 1 until k prime. So of course s and t, s which runs only until k, and t will be running on disjoint sets of variables. So we can break this down into the two probabilities that we just saw, one for s and one for t. So let's look first at the probability for s being in this interval. So first we can see that s is a linear form on k variables, simply from the definition. That means we can use the Berry-Esseen theorem on s when we notice that the absolute value of ci equals 1 for all of its indices, for all I in k. So that means that sigma, by its definition, equals the square root of k. And we can take tau to be 1 because we assumed that the absolute value of ci is less or equal to some tau, and it would be appropriate to set tau to be equal 1. So now if we plug this into the Berry-Esseen theorem, we get this relationship. We get that the probability of Sx divided by sigma, this is sigma, of being in this interval, this would be Ra, minus the probability of the Gaussian random variable being in the same set, A, is larger or equal to minus some absolute constant times by tau is 1, divided by the square root of k. So if we have this, we can see that it's already starting to look a bit more like this. So let's break this down further. So this is from the previous slide. It's just what we just now got. And so we can see that this is identical to the following relation, where we simply moved this probability to the right, a bit of cosmetics, and of course we plugged in the normal, the CDF for the Gaussian normal distribution. And here we just eliminated the square root of k. And so we get this relationship. Now what we can see is that if t equals square root of k, for example, and we choose a large enough k, and we are allowed to choose a large enough k because this lemma states that there exists some k0 in the natural numbers and so on, so we can choose a large enough k, we get a positive constant that depends only on alpha on this side. Again, because we can immediately see that if we plug in square root of k, we get a constant term that is positive. Again, for a large enough k, it would be positive. So this means that, again, probability of Sx being in this interval is something that can be a positive constant that depends only on alpha. So now let's look at the second term from the multiplication, the one that's for t. And what we can see here is that t is a linear form on alpha k variables. Again, if we recall, t runs from k plus 1 until k prime, so it's alpha k variables. And so again, we can use the Berry-Esseen theorem on t with the sigma. This time sigma will be square root of alpha k, and the same tau equals 1. It's the same, it's as explained for the case for s. And so we plug it in and we get the following relationship. And so once again, if we take t to be equal square root of k again, and for a large enough k, this will also not affect. So we get a positive constant that depends only on alpha on this side. Again, if we choose a large enough k, this will not tip us to the negative. So again, we have another term, the multiplication, the second term, that is constant and depends only on alpha and is positive. So in total, that means that we get that this, what we set out to understand, this is actually larger or equal to this relationship, this multiplication, and we just saw that each one of these is a positive constant that depends only on alpha, this one and this one as well, which means that this inequality is larger or equal to a positive constant that depends only on alpha. So we have proven our lemma that for every alpha larger than 0, there exists some k0 in the natural numbers. We can choose one that's large enough, and positive epsilon, such that for every k at least k0 and k prime at least 1 plus alpha k, all signed k prime majorities are epsilon far from signed k majorities. So now we're ready to look at theorem 112 for signed k majorities, and it states the following. So fix a constant gamma in the range 0 to 1, not inclusive. So for any k less or equal to gamma n, testing signed k majorities with one-sided error requires at least omega of k divided by log k queries. So we will prove again via a reduction from the gap equality. So we set k prime to be equal to k divided by 1 minus gamma, and then psi will be the combining operator that takes functions f and g from minus 1, 1, and to the range between minus k prime plus 1, and so on until k prime. Okay, it contains only these elements, the range, and it will return h, which is defined to be the sine of fx plus g of x divided by 2. And we will also define the following communication game. So this communication game with this notation means that Alice and Bob receive f and g, and their goal is to test if h, which is psi of f and g, is a signed k majority or far from a signed k majority. So by lemma 2.4, which we are already familiar with, we have the upper bound of the log of the size of the range, which we saw 2k prime plus 1 for 0. Okay, so it ran from minus k prime until k prime, and we have 0 in the middle, so we have 2k prime plus 1 times by the one-sided query complexity of testing k majority. So this is larger or equal to the communication complexity, the one-sided communication complexity of the corresponding communication game. So by lemma 2.7, we already know for GEQ, one-sided GEQ, with k prime and gamma k prime, and we know that it is omega of k prime. So all we need to show again is to relate between this and this. So that means that if we want to get a lower bound for the query complexity of testing k majority, we need to show this relationship. So the inputs to the GEQ problem with k prime and gamma k prime will be A and B, which are strings of size k prime that take values in 0 and 1. So A is for Alice and B is for Bob. And Alice and Bob, they generate functions f and g from minus 1, 1, and to the range that we saw earlier. So they do that as follows. So f of x is defined to be the sum over the k prime variables with coefficients minus 1 to the power of ai. So this could mean that the coefficients either are minus 1 to the power of 0, which would be 1, or minus 1 to the power of 1, which means a coefficient of minus 1. So it's either minus 1 or 1. The same thing for Bob. G of x is defined very similarly, except instead of ai, we have bi. So we notice that fx plus g of x in this case is the sum of, well, simply we sum across the coefficients here. So we will soon see what that means in our terms of signed k majorities. So again, fx plus g of x is just the sum of the variables with the coefficients that are summed for Alice and Bob, from Alice and Bob. So therefore, what we can do is we can now write h of x as the sine of wx with these w's. Why? Because again, we take the h of x is defined to be fx plus gx divided by 2. So what we can see is that if ai equals bi equals 0, what we get is that each of these is 0, and so we have 1 plus 1 equals 2, divided by 2, of course, because of the definition of h that we just saw, we get 1. So similarly, if we have ai equals bi equals 1, we have minus 2, and then divided by 2, we get minus 1. And of course, if they are not equal, then they cancel each other out, and we get 0 anyway, so 0 divided by 2 remains 0. Okay, so we can see now that hx can be defined in this form that we just described. So when a equals b, what we can see is that all the wi's are non-zero. Why? Because we can see that we're either here or here when they are equal. And so we have wi's that are non-zero. So in this case, h is a signed k prime majority function. Again, because we have k prime variables and all the wi's are going to be non-zero. So what happens when the Hamming distance between a and b equals gamma k prime? In this case, we know that ai equals bi on exactly k prime minus gamma k prime, which equals k, indices. Now, why this equals k? I'm reminding you k prime equals gamma equals k divided by 1 minus gamma. So in this case, we can see that h is assigned k majority. So now we will want to use Lemma 6.1. So before that, we will just show that k prime is indeed equal to 1 plus some positive alpha times by k. And so indeed k prime is defined from the definition. We can get this with some minor algebra. So I'm reminding you that gamma is in 0, 1, in the 0, 1 range. And so this is always going to be positive, and indeed we get that k prime equals 1 plus some positive alpha times by k. So by Lemma 6.1, we know that signed k prime majority functions are a constant distance from all signed k majority functions. So that means that Alice and Bob can use their protocol for this communication game we defined for k majority functions in order to solve their instance of gap equality. So this reduction immediately gives us this relationship that we were looking to obtain. And we also immediately get this relationship with this lower bound, okay, from the query complexity, the one-sided query complexity, and this lower bound. So if we do a bit of algebra, we get the following. We get that the one-sided query complexity for testing signed k majority functions is at least as large as omega of k prime divided by log k prime. Okay, we just divided by this. And of course, k prime is theta of k, so we immediately get what we were looking to obtain for this theorem. So we saw that communication complexity can provide low bounds for property testing. And specifically in this paper, we saw that the authors were able to use their new method, which was to reduce from communication complexity problems to property testing problems, in order to obtain new proofs, and sometimes new proofs that are tighter, that have tighter lower bounds. And we already saw tighter lower bounds were obtained for the relaxed k-Junta, the one that Fisher et al. Asked about in 2004. But more importantly, they were able also to obtain tighter lower bounds for monotonicity. So previously, monotonicity testing had omega log n for non-adaptive and omega n for non-adaptive one-sided. And here we got this lower bound, and this lower bound was valid, that we saw the proof for, was valid for this range. This range was included, this size of range was included in the proof. So if we look at the literature, we can see that the upper bound for this is O of n log size of R, and this is by Goldreich et al. In 2000. And this means that for this range, we cannot improve by more than a logarithmic factor. And this is a major contribution of their paper. Other tighter lower bounds were obtained for submodularity, size S decision trees for the one-sided case, and the signed k majority one-sided case. So we can conclude that sometimes what might seem difficult in one field might be easier through another. Thank you.